Hi folks, Dr. P here. This is Math 20-2 Quadratic Functions, Topic 1, Domain and Range in your workbooks. So in this activity here, we're going to be exploring the domain and range for various functions. In graph 1, we have a straight line, straight function, a linear function that ends with these two solid dots. These two solid dots indicate that those two endpoints are included in this function. So it means that this function is defined exactly at those points. What we're going to do here is we're going to start by writing down the coordinates of those two endpoints. So the coordinates, the x-coordinate over here is -2. The y-coordinate is -5. On the right-hand side, the x-coordinate is 4. And the y-coordinate is 1. So what we want to do here is, in question number 1, we want to determine for what values of x this function is defined. Well, it's defined between x equals to -2 up to and including x equals 4. So the way we're going to express this is using inequality symbols. And we're going to start by indicating what our variable is. Our variable is x, and x has to be greater or equal to -2 and smaller or equal to +4. This expression here is a double inequality, and it represents what's called the domain. So let me just move this here. This here is the domain of this function. So the domain of a function identifies between which values of the independent variable, in this case x, the function is defined. Let's have a look at the y values. So what we're going to look at is what's the smallest and largest possible y value here. Well, the smallest y value is -5, and then the function is defined up to y equals +1. So y has to be greater or equal to -5 and smaller or equal to +1. This is called the range of a function. So the range of a function indicates between which values of the dependent variable, in this case y, the function is defined. Let's have a look at the next example here. In this function here, instead of the two dots at the end, we have these arrows, which means that this function actually continues. On the left-hand side, it goes to -infinity along the x-axis. So over here along the x-axis, if we continue to the left forever and ever, we'll end up at -infinity. If we go the other way, we continue to the right, we're going to end up at +infinity. Same sort of idea along the y-axis. If we continue going down, we are going to be approaching, sorry, not positive, -infinity. And if we continue going up here, increasing the value of the y-axis, we're going to be approaching +infinity. So to the left here, this function continues, and so along the x-axis, it's going to be going towards -infinity. Along the y-axis, it's going to be approaching +infinity. So the domain here, so the valid values for the independent variable x is going to be from -infinity all the way to +infinity. Another way of expressing that is to say that x can be any real number. Any number we will encounter in this course will be a real number. So real numbers include positive numbers, negative numbers, whole numbers, decimals, irrational numbers, fractions. All numbers we'll encounter in this course. So the way we can say that x can be any real number is that we say x belongs to the set of real numbers. This is the mathematical notation for that. the way you read this is x belongs to the real numbers. So that's the domain. For the range, it's going to be the same thing. For the dependent variable, the y variable here, we're going from negative to positive infinity. So we're going to say that y belongs to the real numbers. Look at the next example. This time we do not have a linear function anymore. This is a parabola, but we're going to do the same exercise here. For the x values, so we're going to define the domain here. So again, we have arrows at the left and the right hand side, which means that if we extend this quadratic function, this parabola, on the left hand side like that, and we do that forever and ever, x is progressively is going to become smaller and smaller. If we do the same thing on the right hand side, we extend this forever and ever, x is progressively going to become larger and larger. So again, x is going to be going from negative infinity to positive infinity, which we would write as x belonging to the set of real numbers. What about the range? Well, the smallest possible value for y is going to be negative infinity. If we extend this curve on the left or the right hand side, it's going to be going to negative infinity along the y-axis. Okay. What about this largest possible value for the y variable? Well, the largest possible value the y variable will ever take on is right here, right? Because this function y increases as we go here, and then it flattens out right there where it's crossing the y-axis. Y equals to 3. That's your y-intercept. And then as we continue, now y is becoming smaller because we're going down. So y equals 3 is going to be the largest y value this function will ever attain. So the way we would express that here is that we would say that y is less than or equal to positive 3. It will never be larger than 3. Have a look at the next example. We have a parabola again. So for all quadratic functions, all parabolas like this, the domain will always be x belonging to the set of real numbers. And for the y values, the range, well, in this case, the smallest possible y value is going to be down here, -4. And then it goes up to positive infinity. So we would say that y is greater or equal to -4. It will never be smaller than -4 because the function turns around at -4. Let's move on to, we're at example 1 on page 7. And here we're going to be stating the domain and range of a number of graphs. In the first graph here, we have a function. We have dots at the two ends, which means it ends. There are no arrows here. So for the domain, we would say, so what we want to do here is we want to first figure out the coordinates of these 2 points. So the x coordinate on the right hand side is going to be at the end point. On the right hand side, it's going to be 3. The y coordinate is 0 because we're on the x-axis. On the left hand side, the x coordinate is 0 and the y coordinate is 4. So for the domain, what are the possible, for what values of x is this function defined? We're going to use a double inequality. We're going to say that x is greater or equal to, well, the smallest possible x is going to be 0. And then x is less than or equal to, and then largest possible x is going to be 3. For the range, now we're looking at the y variable. y is going to be ranging between 0 and 4, 0 being the smallest value, 4 being the largest value. So we would say that y has to be greater or equal to 0 and smaller or equal to positive 4. In the next example here, we have a parabola again. And we have arrows at the end. The smallest possible y value is right down here. It's going to be -3. Okay, so for the domain, x belongs to the real numbers. For the range, well, the y value will be -3 or greater. We would say that y is greater or equal to -3. Here we have another parabola, this time going the other way around. Again, we have arrows at the end. This time we have a maximum y value, which is right there. So y equals 2. Again, the domain is going to be x belongs to the real numbers. And for the range, we would say that y is less than or equal to +2. And then a final one here. This time we have a function with dots at the ends. Let's write down the coordinates of those 2 points. So the x coordinate on the right hand side is 4. The y coordinate is also 4. The left hand side, the x coordinate is 0 and the y coordinate is 0. So for the domain, well, x is defined between x equals 0 and 4. So we would say that x is greater or equal to 0 and less than or equal to 4. The range, the smallest value for y is 0, the largest one is 4. The range is going to be the same. Y is greater or equal to 0 and smaller or equal to 4. We are going to skip the next page here and we're going to move on to a word problem on page 10. So stating the domain and range in a real life situation. So in A, we have the graph of the following relation. F of x equals -4.9 x squared plus 12. They've already graphed it for us. It's hard to see, but we do have arrows at the end of this graph here. Means it continues. And then in the first question here for the graph above, state the following in symbol notation. So domain, so what are the smallest and largest possible value for the x variable? Well, it's going to be x belongs to the real numbers. The range, well, the maximum value for the y variable is 12. So y is going to be 12 or smaller. So we're going to say y is less than or equal to 12. So that's your domain and your range. Now what we're going to do here is we're going to take this function and put it into a real life context. Okay, so in this context here, we have in southern Alberta near Fort Macleod, you will find the famous head smashed in buffalo jump. In a form of hunting, Blackfoot once herded buffalo and then stampeded buffalo over the cliffs. If the height of a buffalo above the base of the cliff, h in meters, can be modeled by the following function. H of t equals -4.9 t squared plus 12, where t is the time in seconds after the buffalo jumped. How long was the buffalo in the air to the nearest 100th of a second? Okay, so what you need to notice here is that this function here is the same function that we had up here. They've just named the variables differently. Instead of x, we now have t for time, and instead of calling the function f of x, it's now being referred to as h of t. T is time and h represents height. So we're going to use the graph that they've already graphed for us, and what they are asking us to do is they're saying only a portion of the graph above is appropriate for this situation. In this context, state the restrictions in symbol on interval notation. We're not going to do interval notation. We're just going to do the symbol notation for the domain and the range. So let's go back to this graph we have up here. So I'm going to relabel this. So with the buffaloes, on the x-axis, we have t for time, and it's in seconds. And on the y-axis, I'm going to call it h of t. That's our height in meters. And so this is a Cartesian plane. We have the 4 quadrants of the Cartesian plane here. We have quadrant 1, we have quadrant 2, quadrant 3, and quadrant 4. And in this context, it turns out that this function is not relevant or is not defined in all of the quadrants. Okay? In quadrant 1, what this function shows us is the height of the buffalo above the ground after a certain number of seconds. At time 0, so this is when it just jumps off right there, it's going to be 12 meters above the ground. After 1 second, it's going to be somewhere between 6 and 8 meters right there. And somewhere between 1 and 2 seconds, it's going to hit the ground. It's 0 meters above the ground. So this portion of the curve makes sense in this context. However, on the left-hand side, all of this here and the graph that goes through quadrant 2 is not relevant in this context, because within quadrant 2, time is negative, t is negative, and we cannot have negative time. Quadrant 3 would also not make sense in this context, because within this quadrant, t is negative, time is negative. Again, it doesn't make sense in this context, but height is also negative. We're below the x-axis. That also doesn't make sense in this context, unless the buffalo actually sort of hits the ground and continues below ground, right? And then in quadrant 4, time is positive here, but the height is negative. And again, that's not going to make sense in this particular context. So in this context, with the buffalo falling off the cliff, only this portion of the graph is going to make sense. Okay? So when we're asked to describe or define the domain and the range, the domain and the range will only be defined for this portion of the graph. Okay? So let's have a look at the domain. This time the variable is called t, for the independent variable. What's the smallest possible value for t, for time? Well, it's going to be 0. So t has to be greater or equal to 0. And what's the largest possible value for t? Well, if we take a look at the graph here, the largest possible value for t is going to be right there. Okay? So this is when height is 0. Now, we don't actually know what this is. And we can do the calculation on the calculator, and graphing calculator could help us find the value there, x value right there. But for this purpose here, I'm going to just say that this is approximately 1.5 seconds. This is just eyeballing it. It looks like it's about 1.5 seconds. I'm going to use that number here. So I'm going to say that the largest possible value for time is 1.5. For the range, what's the smallest and largest possible value for the height? H. Well, the smallest one is 0. That's when it hits the ground. So h is greater or equal to 0. And at the same time is less than or equal to 12. 12 is that initial height it started out at. It's up here. So this is the domain and range with restrictions imposed on it by this specific context. Okay, and that also explains or answers question C. This specific let's write it out. In this specific context, the domain and range are restricted. And that's a wrap. Until next time, stay safe, stay healthy, and may the math be with you. See you, folks.